These are the notes for AP Calculus on the topic of arc length. So what arc length refers to is the length of a curve. So if we have some curve here, and we want to know from this point here to this point here, what's the length of that curve, and this is what the arc length refers to. So let's see where the arc length formula comes from, first of all. So if we consider an infinitesimal part of the curve, which we call dl, so a really tiny part of this, even smaller than that, that's what from there to there represents, then we can make it a little triangle, right triangle by considering there's, well, to go from this point to this point, there must be some change in x, infinitesimal small change dx, and some infinitesimal small change in y, we'll call dy. So first we can use, since we've got a right triangle there, the Pythagorean Theorem, and say dl squared, hypotenuse squared, would equal the sum of the legs squared, so dx squared plus dy squared. And eventually we want to use this to figure out an equation for L, the length of the curve. So we can start by dividing both sides of the equation by dx squared. So divide all these by dx squared. And then this one we can actually rewrite. Instead of dl squared over dx squared, we can just make that dl dx squared. The dx squared divided by dx squared is just 1. And the same thing here, we can write this as just dy over dx squared. And then to get rid of the square, to help us solve for L, we can next take the square root of both sides. So then all we have left over here is just dl dx equals the square root 1 plus dy dx squared. And then we can multiply both sides by dx to separate the variables. So we'll have dl equals the square root 1 plus, and another way of writing dy dx, the derivative in function notation, is f prime of x squared dx. And then to get back to L, now that we've got the variable separated, x is on the right, L is on the left, we can integrate both sides. Well, here we've just got a 1 in front of the dl, so that would integrate to just be L, which we're looking for. It would be integral square root of 1 plus f prime x, the derivative squared, times dx. However, if we just leave it like this as an indefinite integral, we wanted the length of some curve that goes on forever, well, that's always going to be infinity, would be the length. But we're just looking at it from point A here to point B. We'll get the x coordinate where that length starts and stops, so it turns into a definite integral from A to B. And that's what gives us the arc length formula right there. So the exact length of it, notice it only works though for a smooth curve. The reason why, if it's not smooth, if you have a corner or a cusp in there that makes it not smooth from A to B, then the function would not be differentiable there, in which case the derivative here, f prime x, would not exist, hence the formula wouldn't work. The derivative doesn't exist somewhere in A to B. So just for smooth curves. All right, now let's take a look at how we apply this formula to some different problems. So determine the arc length of the curve f of x equals x to the 3s from x equals 0 to x equals 4. So the length, sometimes it's referred to length or sometimes arc length, same thing. Be the definite integral from 0 to 4. So we can see the graph of it right here. Here's the graph of x to the 3s. So we're finding the length from right there, x equals 0, to right there where x equals 4. And start off with the square root of 1 plus, and now we need the derivative, f prime of x, and then squared. So we can find the derivative of f of x, f prime of x, using the power rule would just be 3 halves x to the 1 half. Or another way of writing that in radical form, that'd be 3 halves x to the 1 half is the same as the square root of x. So if we put that in here, 3 halves square root of x, but then it's squared, and then times dx. Okay, that would give us our arc length once we work that out. And this one we can do without a calculator. So from 0 to 4, if we just simplify that, it's easier if we square that out. If we square out the 3 halves, that's 9/4. And square root of x squared is just x. And then in order to integrate this, we have to use the technique of u substitution. Notice we have a function inside the square root, so we can set u equal to 1 plus 9/4 x. But since this is a definite integral, and we'll use u substitution on a definite integral, you have to convert your lower and upper limits to be in terms of u. So if you substitute in 4 for x, well, that counts before right there. That would just be 1, so that would just be 9 plus 1 gives you 10, will be our upper limit. And when you substitute in 0, that wipes out the 9/4, gives you just 1. Very low limit. And then we can just rewrite this as the square root of u. But we also need to get rid of the dx. So remember the way we do that to get it in terms of du is to take the derivative of what you say u equal to. So du dx here would just be 9/4. And then if you cross multiply there, you get 9 dx equals 4 du. Divide by the 9 gives you dx equals 4 du over 9. And then we can substitute that right in here for dx. And then to make the integral simple, we can pull out the constant of 4/9 on the outside. Integral from 1 to 10. And to make it easier to integrate, instead of the square root of u, easier to integrate if you write it in rational exponent form is u to the 1 half times du. So now we've turned it into a simpler integral, all in terms of u that we can actually integrate. So then the antiderivative of u to the 1 half is u to the 3 halves using the power rule. Divided by 3 halves is the same as multiplying by the reciprocal of 2/3. Evaluated from 1 to 10. And you can also pull out the 2/3 times the 4/9 that's already out there will give you 8/27. And you can simplify it to make it easier to substitute in. You can rewrite u to the 3 halves as this in radical form as the square root of u cubed. 1 to 10. So we've got 8/27. Then if you substitute in the upper limit of 10, it would be the square root of 10 cubed minus, if you put in the lower limit of 1, it would be the square root of 1 cubed. So square root of 10 is now a perfect square. However, since it's cubed, to make it a little simpler, if you squared, it would just be 10, and then there'd be one more radical 10 left. And the square root of 1 is just 1, cubed is 1. Okay. So you can leave it like that, or if you want to distribute out the 8, you can make it 80 root 10 minus 8 all over 27 if you want. So that would give us our arc length. Now if you want to, you don't have to put this, but to remind yourself it's a length, not an area or volume, you could just put units. So if this represented 1 inch, then it would be that many inches. If this represented 1 centimeter, then it would be that many centimeters, and so on. Okay, so now let's take a look at one with the use of a graphing calculator. And you don't actually have to graph these. I just did that on the first example there, so you can see visually what we were actually finding. But this time we want to write and evaluate an integral expression that gives the arc length of the curve y equals arc tangent of e to the x squared from x equals 1 to x equals 5. So the length here, or arc length, the integral from 1 to 5 of the square root, 1 plus, and again we need the derivative here. So, in order to take the derivative of arctangent of e to the x squared, we have to use what I call the double chain rule. So we have two functions inside. We got e to the x squared is inside arctangent, and x squared is inside the exponent of e. So, remember you start on the outside and you work the way in, so the derivative here, dy dx. Start with the derivative of arctangent. So normally it's 1 over 1 plus x squared, but in this case it's not x there, it's e to the x squared. So we'll have e to the x squared. That's the derivative of arctangent. Then you take the derivative of the next function inside, which is e to the x squared. Well, that just stays the same, e to the x when you take the derivative, so that's just e to the x squared. But finally you need the derivative using the chain rule of x squared, which is 2x. So if you want, you can simplify that just a little bit. You can make it on the numerator 2x e to the x squared over 1 plus e to the, if you square that, as you're multiplying the exponents when in parentheses, that'd be e to the 2x squared. So that's what we would have in here. 2x e to the x squared over 1 plus e to the 2x squared. Remember, that is also squared the whole thing. And then times dx. So you can see this one would be extremely difficult to integrate by hand. So let's go ahead and integrate it using our graphing calculator. So first I'll show you using a TI 8384. So you would just first go math, down to number 9, function integrate. And you just got to be really careful with your parentheses here, because there's going to be a lot of, keep track of them. For every open parentheses, make sure you have a corresponding closed parentheses in the right place. So first we need the square root. And then it already puts a parentheses for us there, for what's inside the square root, so 1 plus. And then we need another parentheses right here for the one in orange there, because we're going to square that whole thing. And then we've got 2x, the e to the x button is right here, second, and then on the natural log, the e to the, notice it does another open parentheses for the exponent, which is x squared. So then we need a closed parentheses for the exponent. And then a divided by, but notice there's two things on the denominator, so we need another open parentheses to make sure it divides by both of those, not just the 1 here. So 1 plus second e to the x. Here's another open parentheses for this exponent, which is 2x squared. Close parentheses on the exponent, then close parentheses on the denominator. Then another close parentheses for the orange one right here, and then we're going to square that. And then we need a close parentheses on the square root, since the whole thing is inside the square root. And then you put a comma x, comma the lower limit's 1, comma the upper limit's 5. And then a close parentheses for the integral function. And if you didn't put all your parentheses in the right place there, you could get the wrong answer, or it could give you an error if you don't have matching the same number of open parentheses as you do closed parentheses. So we get 4.068 or 4.069. If you round it. So if you truncate it, it's just 4.068, or if you round it, 4.069. And again, this is just a length, so if you want to, you can put units on this. Now let's see how we could work this out if you have a TI Inspire graphing calculator. A little bit easier on the Inspire. So you could just go New Document. We just need a calculator here. And then you just go hit this button for the definite integral from 1 to 5. And then we have the square root, which is right here. 1 plus, and then a parentheses. So we're going to square that whole thing. It does a close parentheses automatically here. And then here you can put the fraction in there. Okay. So then we had 2x e to the x squared on the numerator over 1 plus e to the 2x squared. The denominator. Then this arrow and this whole thing was squared, and then dx. So it looks more like what we wrote down on Inspire, makes it a little easier. And you can see we get the same answer. Okay, let's take a look at a couple other examples here that will not require the graphing calculator. So this one says, region R is bounded by the x-axis, the y-axis, the vertical line x equals 4, and the curve y equals e to the 3x. Write but do not evaluate an expression involving integral that gives the perimeter of region R. Okay, so that's what we're looking for. So let's start by graphing our vertical line here. We've already got the x and y-axis on here. So the vertical line x equals 4. Graph right here. X equals 4. And then the other curve we want to graph is y equals e to the 3x. So if you plug in some easy points, if you substitute 0, e to the 0 is just 1, so it goes right here, where it touches the y-axis. And just like other exponential functions, it increases, but it increases a little faster than them. If you plug in 4, we get e to the 12th, which is really big. So it doesn't have to be a perfectly accurate graph. I'm not going to make it as high as e to the 12th actually is. I'm just going to curve it up so we can see the general shape of our region enclosing. Okay, so to get the perimeter, let's start with the straight lines first. So the length of this side, so this is region R here. So the length of this side here, since the y-coordinate is 1, is just 1. The length of the base from 0 to 4 is 4. To get the length on the red side right here, well, remember when we plugged in 4 here, that give us e to the 12th. So that would be the y-coordinate right there on the graph, and that means that would be the height, e to the 12th. And then the last part, we just needed to use our arc length formula. So if we start adding these up, we get 1 plus 4, which is 5, plus, this side is e to the 12th, plus, and that's where we need arc length formula, the definite integral from, in this case, x equals 0, that's where that starts, to x equals 4, that's where it stops. And then we'd have the square root, 1 plus, then we need the derivative of our function, so it's not too hard here, dy dx, just using the chain rule here, the derivative of e stays the same. Using the chain rule, the derivative of 3x is 3, so 3e to the 3x. So 3e to the 3x squared, and then times dx. Now if you want to, you can square this out and make it 9e to the 6x, that's fine, or you could just leave it like that. Notice this one says write but do not evaluate an expression involving an integral that represents the perimeter. So this would be the perimeter of region R. All right, let's take a look at one more example, a little bit different here. This one says the length of the curve is given by this definite integral here. And if the curve contains the point -1, 7, write an equation for the curve. So it's kind of working in reverse. We're given the length of the curve formula, and we're trying to find what an equation for the curve could be. So the way to start this out is think, well, we're going from -2 to 1, square this. So the equation for the curve could start with right here. Remember the formula, that equals f prime of x squared. So we know f prime of x squared would equal 9x is 1. Then, to get back to f of x, the curve we're looking for, first to get rid of the squared, you can take the square root of both sides. that'll give you f prime of x, square root of 9 is 3, and square root of x to the fourth is x squared. Now technically when you take the square root of both sides, normally you put plus or minus, so it could be either positive or negative. But notice it says write an equation for the curve, not the equation for the curve. So there's more than one possible right answer, but it's easiest probably to use the positive version of it. But if you put negative, that's fine also. Then, if you just multiply both sides by dx, then that'll allow you to find the antiderivative of both sides, to integrate both sides. So when you integrate f prime of x, you get back the original function f of x. When you integrate 3x squared using the power rule, you get 3x cubed over 3. And then, since these are indefinite integrals, we need an unknown constant plus c. So f of x is just another way of writing y. The 3's reduce out, so you get x cubed plus c. And now all you have to do is figure out what that constant is, and that's why it gives you this point. If it didn't give you that point, that constant could be anything. But since it does, if we plug that substitute in for x and y like you do on the separation of variable problems, you substitute in 7 for y and negative 1 for x. Now we can solve for c. So 7 equals negative 1 cubed is negative 1 plus c. Then just add the 1 over, so c would equal 8. You can substitute that right in there. So what an equation for the curve could be y equals x cubed plus 8. And that concludes the notes for AP Calculus on the topic of arc length.